Hello, welcome back. This is Calculus by Dr. Oz. Today in this video, I'm going to try to have a short revision of Chapter 2 sections that we covered in the lecture videos. And hopefully I'm going to mention about all important results of Chapter 2 in this video. So if you want to have a detoured revision of important results covered in Chapter 2, this video is just a good fit for you. After you watch this video, you're going to make sure that you have all the skill sets necessary to achieve the course learning objectives corresponding to Chapter 2. All right, the first slide is about the limits that fail to exist. We have three common behaviors. In the first case, f approaches a different number from the right side of the limit point c, then it approaches from the left side, so left and right limits, in other words, are not equal. And in the second case, f increases or decreases without a bound, which essentially means that f either approaches plus or minus infinity, and we call those cases as like doesn't exist. But if you want to quantify them, you can just write plus or minus infinity for those limits. And in the last case scenario, if f oscillates from one fixed point to another one as x approaches c, it's likely that the limit is not going to exist. So f may not be defined at the limit point, but if it's defined at the limit point c, so why not using the direct substitution? So here we go. We use the direct substitution to evaluate the limits as long as c is in the domain of the function. And in fact, for some basic or elementary functions, you have the limits provided here. So limit of a constant, limit of x, limit of x to the power of n. These are all determined in this result here, and check for your own reference. And we also define the properties of limits. So if you have two functions, f and g, having limits L and k, then you can talk about the first function multiplied by a scalar, like b times f of x. So the limit of that is going to be b times the limit value, capital L. You can talk about the sum or difference of these two functions and their limits. And you can talk about the limit of the product, limit of the quotient, limit of the function raised to power of n. So in all different cases, you have those like nice properties, especially when you go through examples, you can use each of those properties. And the next two results are very important if you're working with polynomial and rational functions. Well, first of all, direct substitution is awesome for a polynomial function, so you don't need to have graphical aid, or you don't need to have a table of sample values. For a rational function, the only thing that you care about is that you're going to be careful with the denominator at the limit point. If it's not equal to 0, you're safe with the direct substitution. So direct substitution is applied mostly in exercises, as long as the limit point is in the domain of the given function, either a polynomial or rational functions. And if you have a function involving a radical, if you're talking about the nth root of that, but n is odd, so probably function evaluation or direct substitution is the best way. If n is even, just be careful about the limit point. As long as, again, c is in the domain of the radical, then you're safe with direct substitution. The next two results are about the limit of a composite function and limits of transcendental functions. Again, if you have a composition of two functions, as long as those individual limits exist, you can use direct substitution. And for transcendental functions and even trig functions and logarithmic and exponential functions, as long as the point c is in the domain of these functions, you can do direct substitution. So to sum up, in fact, for so many known elementary functions, if you check the domain and if c belongs to the domain, direct substitution is the best way to handle the limit problems. And this slide is for honors section, so this is the official definition of limit, or in other words, we call it epsilon delta definition of the limit. So here the catch is that epsilon is sort of like given arbitrary to you, and you're determining delta based on the epsilon, which essentially means that so if you look at the neighborhood of the limit point, let's say like the epsilon neighborhood of that, which is provided to you, then the corresponding delta neighborhood in the x-axis should depend on what you start with, the epsilon. Okay, so if you can prove this dependence, then that means the limit of the function as x approaches c is equal to L. Again, this is only for honors section. If you're just standard 136 student, you can skip this part. We talked about strategy for finding limits, and one strategy is coming along with this result here. So if you come up with a function that agrees with the given function everywhere except the limit point, so the limit of the original function is the same as the limit of the function g, which agrees with your function everywhere except c. So essentially this comes out of different ways. We're going to see in a few minutes that, for example, dividing out technique provides you a function that agrees with your function, or rationalizing is another technique. And here is a strategy for finding the limits. So first of all, if the direct substitution works, why don't you go with that? So as long as c is in the domain of the function, you should try that one first. If you cannot use the direct substitution, then try to come up with another function, g, that agrees with the function everywhere except c, as I mentioned in this result here. Okay, and if everything fails, here, then use the graphical aid or table of sample values to reinforce your conclusion. But again, you always start with direct substitution. If that doesn't work, then you're going to try to find a similar function that agrees with the original function. If everything fails, then going back to the basics, so you're going to use the graphical aid or table of sample values. So we learned about the dividing out technique to come up with a similar function that agrees with the original function. It's all based on simplifying the provided rational function, so that the resulting function is something that you can easily calculate the limit by using the direct substitution. So this requires skills from algebra, obviously. So you have to know how to simplify polynomials, how to factor them out. So if you are good at that, and this should be like a good strategy for you. And generally this technique is applied whenever you have 0 over 0 type forms as you plug in the limit value into the rational function. So if this is happening, then probably dividing out technique could be one of the ways to follow. And another technique to come up with a similar function is called the rationalizing technique. And this also happens when you have 0 over 0 type indeterminate forms. So all you do is just multiply the rational function by the conjugate of the numerator or denominator. And we have gone through lots of examples here. And you had the homework problems. Please revisit them because there are different forms of that popping every time. So in this particular case, the radical term pops at the top, so we had to multiply the top and the bottom by the conjugate of the top. We also talked about a very important result of calculus called the squeeze theorem, or in another context, it's called the sandwich theorem. So to be able to use the squeeze theorem, you have to come up with two functions that squeezes the given function. In other words, these two functions h and g should satisfy this inequality here. So as long as the graph of the original function f is in between the graphs of h and g, you can use the squeeze theorem, but you have to prove that the limits of the outer functions here, f and g, should be the same. Okay, if you can prove that the outer limits is equal to capital L, so the inner limit, which is what you're after, has to be also L. Okay, so to sort of like to be able to use the squeeze theorem, you should sort of like majorize and minorize f of x, and we had good examples for that in the lecture videos. Please watch them and go through the homework problems to see different case scenarios. A natural outcome of the squeeze theorem is the result here. So you have three special limits, and you're supposed to know each limit, by the way, because you're going to be tested on each of those limits, and you can put those in your formula card if you want to. So you have sine x over x at 0, that's 1. 1 minus cosine x over x at 0, that approaches 0. And here you can take this as the definition of the number, the transcendental number e, so which is in fact the limit of 1 plus x to the power of 1 over x as x approaches 0. We also talked about continuity at a point and on an open interval. So you can take this as the definition of continuity at a point and on an open interval. And specifically for the continuity at a point, you have to check if all three conditions are satisfied. So C must be in the domain of the function. Limit of the function should exist at the point C, and the limit value should be exactly the same as the function's value attained at C. So if all three conditions are satisfied, f is continuous at the point C. And if you're given an interval, and if you check the continuity on an interval, you have to check the continuity at every single point. That means at every single point, these three conditions are supposed to be satisfied. So take this as the definition of the continuity on an open interval. In fact, we have all three cases here that in fact violates each property mentioned in the definition of continuity. Please check these graphs because these are good representative graphs to understand each piece in the definition of the continuity here. We also defined cited limits, and therefore we defined the continuity on a closed interval. So in fact, the existence of a limit is relying on the equality of the cited limits. So we used a special notation, C superscript negative sign and C superscript positive sign. These are referring to cited limits. And again, for a function to have a limit at a point, cited limits should exist and should be equal to each other. And specifically for closed intervals, if you are checking the continuity, you should look at the cited limits at the endpoints, but for the left end, you should look at the side limit, so the right-sided limit, what I'm trying to say here. And for the other endpoint B, you should look at the left-sided limit, and if they exist, then and if they are equal to the function's values attained at those endpoints, so you have also the continuity at the end points of the interval. We had also properties of continuity, so multiplying by a scalar, looking at the sum or difference of two functions, product of functions, and quotient of functions. Please check those properties and use them accordingly. As well, we had all elementary functions discussed in pre-calculus. So as long as the point of consideration or the interval of consideration is in the domain of each polynomial, rational, radical, trig, exponential, and logarithmic functions, so you have the continuity in your pocket. So for that reason, it's important to remember especially the domains of trig functions, and as well the logarithmic function ln x. So one of the discussions that we had in earlier videos was the intermediate value theorem, which is the application of continuity of a function. So you're going to be tested on this in probably the exams and quizzes. So it's better to check if all two conditions are satisfied before you apply the intermediate value theorem, because this theorem says that if you have a continuous function to start with on a closed interval AB, and if f attains different values at the endpoints, then every intermediate value between f of a and f of b should be achieved by at least one number c coming from this interval here. So this is again called the intermediate value theorem, and it's very important to know how to apply this theorem, and mostly it's applied to find zeros of functions. And finally, we talked about vertical asymptotes and infinite limits specifically. If f of x approaches infinity or minus infinity as x approaches c from the right or the left, then we call that x equals c is a vertical asymptote to the graph. And I gave you a good strategy for finding vertical asymptotes for rational functions. So when you have f and g here at the top and the bottom, so all you're going to see is, all you're going to do is in fact to find c's that make the bottom zero but not the top. So if you can pinpoint those points, those are going to be the candidates of vertical asymptotes. And once you pinpoint a vertical asymptote, let's say once you pinpoint C, then you're going to check cited limits at C to reinforce the existence of vertical asymptotes, because just saying like there's a vertical asymptote may not be enough, and we want to know the behavior of the function on the left of the vertical asymptote and on the right of the vertical asymptote in terms of whether the function is approaching plus infinity or minus infinity. And finally, we had the properties of infinite limits, and we use them a lot in many application problems and exercises, so please refer back to those. And these are all important results of chapter 2, and like every single result here is associated with one of the learning objectives of this chapter. So make sure like you're feeling comfortable with all of these results and you know how to use them towards your homework assignments and quizzes. All right, if you have any questions or comments, please put those down in the comment box on YouTube, and I'll try to address your questions as fast as I can. Thanks for watching. I'll see you in another video. Bye.